Hello, today's video is going to be about CFM demand. And I'm sure you're probably wondering, what's CFM demand? I haven't heard of that. It's basically the amount of air that the engine is going to try and ingest at a given RPM. It's just cubic inch displacement times RPM, and you figure it out into airflow per runner. And that gives you an idea of what the motor is capable of. The reason we look at this is because there are limits to what an engine can do. And you need to decide in your build if what you're looking at makes sense. Now, I've written 302, 350, and 421 small block displacement and figured out the airflow. Now, the airflow is fairly easy to sort out. There's a formula for it: cubic inch displacement of the motor times RPM times 0.009497, and then divide that by the number of cylinders, because that'll then give you CFM per runner, which is what heads are done on. So with the 302, you can see it goes from 35 CFM to 322. Now, back in the day, a power pack head, say, was only like 170 CFM or so. And so that would fall right in here at about 5,000 RPM. Now remember, you have a little bit of carryover, and you can go past peak by saying maybe 1,000 RPM. But that makes about sense with what they used to do with the 302s and the flow that it had with a fairly good sized cam. Remember, this is based on 100% volumetric efficiency. So you are talking about, with these numbers, that's going to be a fairly good sized cam, like a 256, which is exactly what they ran with some of the early motors. So that kind of puts you in the right perspective about why it did what it did. Now, our flows, of course, in heads have gone up over the years. It's easy now to get a small block Chevy head that flows 320, and that's an easy thing to do. But 320 on a 302 is going to bring you way down here to 9,000 RPM. And remember, you'll probably carry over past that. So you're talking about building a 9 to 10,000 RPM engine. Now that's possible, but you're going to need good components. You're going to need a really stable valve train. You're going to need a cam design that will be okay up at that limit. And it's much harder to build. Now, if you take that same 322 and you put it in a 350, you're now talking about like a 7,500 RPM motor. And that's much more reasonable. And we built lots of those, certainly even back in the 90s. And 500 horse, 300 CFM, fairly decent cam, you were ready to go. And it wasn't that hard of a thing. But heads have, like I said, have more and more flow. So you can see that if you do the same thing, 320 on a 421, you're only talking about a 6,500 RPM motor. And so you start to see that the cubic inch displacement makes life easier. It's just better to build the larger displacement motor. And yes, you may have some cost in the components to do that, but the RPM will be down, and you're also not going to have to spend money on such a fancy valve train. It doesn't have to be quite as stable. And if you find heads that flow more than that, if you've already pushed up the cubic inch displacement, you can start to deal with more CFM. And so this is where you go to choose what you're doing. Either you're working from a head that you have found and you know what it flows, or a head that you can afford and you know what it flows. You can be somewhat realistic about what the rest of the engine build needs to kind of look at, because you have some idea of what size it needs to be and what RPM you're going to be looking at. Now, can you use a head that flows more than what this is? I mean, can we take a 320 CFM head but only run it to like maybe 6,000 RPM? And the answer is you can. But you're going to wind up with a curve that's more of a curve. Remember, the torque is technically a flat line. When I made this, I took the CFM demand of the head, I calculated out horsepower to have an idea of where you would sit on horsepower given that CFM at 100% VE. And then I figured that into torque, and if you look, torque comes out as a flat number. The reason is the torque is really what's generated by the cubic inch displacement and the fill of air. It's just whether or not you generate it at a higher RPM. As the cycle time goes up, you need more and more flow in order to keep up with what the engine is doing. You're still generating the same torque, but you're generating it at a higher RPM, which then generates more horsepower. Now the torque basically comes out to 1.297 per cubic inch. That's your basic number. Now that's based on 100% volumetric efficiency and 8-to-1 compression. Now the one thing that doesn't affect airflow is compression. It works in adjacent to airflow. So as you go up in compression, you will gain horsepower and torque, but you also may require better and better fuel. If you go from 8-to-1 to 9-to-1, you're going to gain about 3%, about 3% per point. So if you're going from 8-to-1 to 10-to-1, you're gaining about 6%. Now, in a race car, that's okay, and you gain it everywhere, all across the torque curve. So across your whole power band is where compression helps. The problem is, if you're building a truck motor, you don't really want a bunch of compression or the need for really high quality fuel. So you kind of keep the compression down. And when you do that, you start looking that the cubic inch displacement is a better choice. Because as we went up in cubic inch, we went from 382 to 453 to 546 in torque. You add in maybe just 1 point of compression, gain another 3%, and you have a pretty good truck motor, especially if you can keep it down here in the lower RPM. Now, back to that head. If you run, say, a 320 CFM head on a smaller motor, what happens? Well, instead of having a flat torque curve like we've been looking at, what you wind up with is a bell curve. Because at lower RPM, you will not get a proper fill. And that will impact the amount of air going in, which will impact the amount of torque that you make, which impacts the amount of horsepower you make. And so you want this stuff to be fairly balanced. I mean, it's really nice to have a dead flat torque curve when you go to dyno a motor, and it shows that you actually did pretty well. Because the lower RPM can certainly be impacted by overlap of a bigger cam or by pulse back of not having enough airspeed. Both of those conversations are for another video, but they do affect what's going to go up. And so you can wind up with it only doing well maybe in the peak. And you won't really make that horsepower that that head is capable of. You'll be down here making the other horsepower because you're not up there in RPM. And these are the limits that I'm talking about. If you limit the RPM and the cubic inch displacement, you can only make so much horsepower. You won't make use of the good head that you've gone to the trouble of getting. And so you start having to go up in RPM and up in cubic inch displacement to make really good use of those good heads that flow a lot. And that gets to be more expensive. So that's basically CFM demand and why you're looking at it. It'll give you some idea of horsepower. It'll give you some idea of about what you're looking at in RPM, which will also let you choose a cam and what intake you want to run, because remember, you do have to worry about airspeed. And the basic formulas are fairly straightforward. You can calculate, if you have CFM, you can calculate the RPM. It's strictly CFM divided by the constant 0009497 divided by CID times cylinder. That'll give you the RPM if you have a particular head flow and you say, this is what I want to be. What RPM am I going to wind up at? And so horsepower is easy to figure. That has always been 0.26 times CFM times the number of cylinders. You can figure torque strictly by CID, or you can figure the horsepower and go move it over to torque. It'll give you the same basic number. That's CFM demand, and that's why you need to look at it at the beginning of your build to make sure you're not overreaching. Because if you say, you know, I've got this big head and it flows 360 and that's going to give me big horsepower, well, you better find out where that's going to happen. And so take a look at CFM demand in your build. It's really a help to know. If you limit the RPM, you'll hit a wall. It won't make more power, even if you have better intake, even if you have a better head flow, even if you put it on a bigger carb, it just flat stops making power because it just can't ingest anymore. And that's where CFM demand helps. So I wish you all luck on all your builds, and I hope you have a good day, and we will talk to you later. If there's another video we need, or if I need to redo some of this because it doesn't make sense, let me know in the comments, and we will cover more of this. I can certainly cover more about camshafts, about airflow, airspeed. There are some videos. There is a playlist of some videos from my other YouTube channel that show some of this stuff. And like I said, we can easily expand if you let me know what you need to know. So have a good day. Talk to you later.